In this video, we will discuss a new method for describing curves known as parametric equations. Please don't forget to click on the like button, subscribe to our channel and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. So far in calculus, we have mainly represented plane curves using functions of the form y equals f of x or x equals f of y. Most of the formulas we've developed require the functions to be in one of these two forms. However, some curves, like a circle, do not fit into this form easily. For instance, consider a circle. It's simple to write the equation of a circle centered at the origin with radius r. However, we will never be able to write the equation of a circle down as a single equation in either of the forms y equals f of x or x equals f of I, because solving for y gives the equation, and if we graph y, the graph will not pass the vertical line test. This means the equation for the graph of a circle is not a function. We can solve for y as the following two formulas show, and there are two functions. Each formula gives a portion of the circle. Unfortunately, we usually have to work with the entire circle and can focus on just one part of it. Even if we can narrow things down to only one of these portions, the function is still often fairly unpleasant to work with. So to deal with some of these problems, we introduce parametric equations. Parametric equations are a set of equations that express the coordinates of points in the system in terms of one or more parameters. If x and y are given as functions x equals f of t, y equals g of t over an interval I of t values, then the set of other pairs x, y equals f of t and g of t defined by these equations creates a plane curve based on the parameter t. These equations are called parametric equations for the curve. There are several methods to express a rectangular equation as a set of parametric equations as long as the resulting graphs are equivalent over the same domain. The set of parametric equations is valid. If the domain becomes restricted, the graphs may differ. Through some examples, we will see how we can find parametric equations for curves defined by rectangular equations. Find parametric equations for the following equations. An obvious choice would be to let x equals t and determine the corresponding y by substitution. The graph of any function y equals f of x can always be parameterized in this way. But on this channel, we will move away from the obvious and try something more interesting. We can express this quadratic function in factored form. Now you can let t equal x plus 2 or x minus 3. It doesn't matter. If t equals x plus 2, you can determine the corresponding y by substitution. The set of parametric equations is: to graph the curve defined by these parametric equations, we need to create a table of t values and calculate corresponding x and y values. The first column in this table should list the t values, while the second and third columns should contain the corresponding x and y values to be plotted as points on the graph. As t progresses from -1 to 4, the point on the curve moves along a parabola. The direction of the point's movement is referred to as the orientation and is shown on the graph. This equation represents a horizontal parabola equation, and it opens to the right. Start by factoring out the common term. Since to solve this equation for y, the square root would have to be taken, it would be convenient to let x minus 1 equals t squared. Solve this for x. Then you can determine the corresponding y by substitution. The set of parametric equations is: we create a table of t-values and calculate x and y to graph the curve defined by these parametric equations. As t progresses from -2 to 2, the point on the curve travels along a parabola. The direction the point moves is again called orientation and is indicated on the graph. The equation of a parabola can be expressed in various parametric forms because parameterizations are not unique. Converting parabola equations from rectangular form to parametric form using derivatives can be a very useful technique. I will demonstrate how to do this using derivatives. It's important to pay attention to this. In the equation, the parameter t corresponds to a point on the graph where the tangent line has a slope of t. We have learned how to transform parabola equations from rectangular to parametric forms. Now let's turn our attention to converting linear and line segment equations from rectangular to parametric forms. When dealing with linear equations, it's important to understand the three major forms: point slope, standard, and slope intercept. So let us convert this linear equation from rectangular form to parametric form. You can accomplish this in various ways, but I'll show you a quick and efficient method. Solve the equation for the slope. Now set t equal to the numerator. Solve this for y. Then you can determine the corresponding x by substitution. Now we will see how to find a set of parametric equations for the line connecting two points. Find the parameterization for the line connecting the 2 points. If you are familiar with vectors in the Cartesian plane, you can solve this example easily by using the fact that adding a point to a vector gives you another point. From there, you can easily obtain the parametric equations of the line segment. However, assuming you are not familiar with vectors, I will solve this example using a different approach. We start with the point slope form to find the slope. After finding the slope, we write it in point slope form. We can find the y-intercept by using either of the two endpoints, as it doesn't make any difference which one we choose. Once we have the y-intercept, we rewrite the equation in point-slope form and solve for x. As t progresses from -5 to 20, the point on the curve travels along a line. The direction the point moves is again called orientation and is indicated on the graph. We did not restrict the parameter t and assumed that it could be any real number. However, sometimes we limit t to a finite range. For example, if we were asked to find the parameterization for the line segment connecting the points, we would have to restrict t so that the endpoints lie within a certain range. We could write x equals t over 5 and replace x with 1 and then replace x with 4, thus having a range for the values of t. We've already discussed how to parameterize equations for parabolas and straight lines. Now let's explore how to parameterize equations for circles, ellipses, and hyperbolas. Find parametric equations for the circle. The trick here is to use the Pythagorean identity. To do this, divide both sides by 4. We set sine of t equals x over 2 and cosine of t equals y over 2, which gives x equals 2 times sine of t and y equals 2 times cosine of t. To graph the circle once, we need the values of t to be between 0 and 2 times pi. We create a table of t values and calculate x and y to graph the curve defined by these parametric equations. As t progresses from 0 to 2 times pi, the point on the curve travels along a circle in a counterclockwise direction. The direction the point moves is again called orientation and is indicated on the graph. Find parametric equations for the ellipse. We apply the Pythagorean identity again. We set sine of t equals x minus 2 over 9 and cosine of t equals y plus 3 over 4. To graph the ellipse once, we need the values of t to be between 0 and 2 times pi. We create a table of t values and calculate x and y to graph the curve defined by these parametric equations. As t progresses from 0 to 2 times pi, the point on the curve travels along the ellipse in the clockwise direction. Find a parameterization for the hyperbola. We apply the Pythagorean identity, which gives the relation between secant and tangent. We set secant of t equals x minus 2 over 9, and tangent of t equals y plus 3 over 4. To obtain the parametric equations, you solve the first equation for y and the second for x. To graph the hyperbola once, we need the values of t to be between 0 and 360 degrees. We create a table of t values and calculate x and y to graph the curve these parametric equations define. Wherever cosine is 0, the tangent function and secant function are undefined. The value of tangent of t is not defined at odd multiples of 90 degrees. That is, the tangent of t is not defined for t equals 90 degrees and 270 degrees. As t progresses from 0 to 360 degrees, the point on the curve in the right-hand branch travels along the hyperbola in the clockwise direction, while the point on the curve in the left-hand branch travels along the hyperbola in the counterclockwise direction. We began our exploration of parametric equations by approaching them in a way that differs from the usual undergraduate course sequence. I first demonstrated the process of deriving a set of parametric equations from rectangular equations in x and y, and then illustrated how to graph these parametric equations. Now I will show you how to make the reverse process and obtain rectangular equations from parametric equations. This is helpful because sometimes it's easier to visualize a curve in rectangular coordinates than parametric equations. When we have a pair of parametric equations, we may want to simplify them by removing the parameter t and converting them into rectangular form. This is useful when it's easier to visualize a curve in rectangular coordinates. To do this, we can eliminate the parameter t by solving for t in one of the equations, usually the simplest one, and then substituting the result into the other equation. This will give us a new equation in terms of x and y, known as a rectangular equation. Eliminate the parameter t to find a Cartesian equation of the following curves. To find a Cartesian equation for this curve, we must eliminate the parameter t. We typically select the simplest equation to start with. In this instance, both equations appear to be very simple, so we can choose either one. Let's take the first equation and solve it in terms of t. Substitute this value for t in the equation for y. We obtain an equation of a line. To find a Cartesian equation for this curve, we must eliminate the parameter t. We will begin by selecting the simplest equation. In this case, it seems that the second equation is simpler, so we will choose this one. We will then take the second equation and solve it in terms of t. After that, we will substitute this value for t in the first equation for x. This will give us an equation for a horizontal parabola. No restriction was placed on the parameter t, so we assumed that t could be any real number. The graph is shown below. But sometimes we restrict t to lie in a finite interval. For instance, if t is between -2 and 2, to produce the same graph, we should limit y to values between 0 and -4. To find a Cartesian equation for this curve, we must eliminate the parameter t. We will begin by selecting the simplest equation again. In this case, it seems that the second equation is simpler since it does not have the square root. So we will choose this one. We will then take the second equation and solve it in terms of t. After that, we will substitute this value for t in the first equation for x. This gives us an equation for a parabola, which, unlike item B, represents a function. Even though there are no restrictions on the parameter t, we should be cautious and limit the domain of the function, as we cannot assume that t can be any real number. You should note that t minus 3 must be greater than or equal to 0. Therefore, x must also be greater than or equal to 0. To ensure the correct graph, we need to limit x to values greater than or equal to 0. We will begin by selecting the simplest equation. Note that the first equation is simpler since it does not have a log. This gives us a logarithm function. Even though there are no restrictions on the parameter t, we should be cautious and limit the domain of the function, as we cannot assume that t can be any real number. The logarithmic function is defined only when the argument of the function is positive, so x plus 5 is greater than 0 and x is greater than -5. In the second equation, the cosecant is the inverse of the sine, providing a useful shortcut for solving this problem. It gives us a hyperbola equation. We have constraints on the parameter t. When t is between 0 and pi over 2, the sine is between 0 and 1. So y will always be greater than 1. The video introduced parametric equations, which are useful for analyzing motion and important in fields like computer graphics and computer-aided design. In the next video, calculus will be applied to parametric curves to find slopes, length, and areas associated with parameterized curves.